Welcome to DAR Tutors for online and home tuition. Today we're diving into a fundamental concept in probability, discrete random variables. By the end of this session, you will be able to, first, define and distinguish between discrete and continuous random variables. Second, you'll be able to construct and interpret probability distributions for discrete random variables and find their key measures like the mode, median, and expected value. Finally, you will learn to calculate and interpret the variance and standard deviation of these variables, which helps us understand the spread of possible outcomes. We'll begin by addressing an opening problem to illustrate the concepts we're about to learn. Imagine a sideshow game where a player has a 50% chance of winning a prize. The prize values and their probabilities are given in this table. You can win nothing, $2, $5, $10, or $20, each with a specific probability. Let's think about this situation. First, what is the sum of these probabilities? The sum is 0.5 plus 0.35 plus 0.1 plus 0.04 plus 0.01, which equals 1. This sum must be 1 because it represents all possible outcomes. There are no other options. Second, what is the most likely outcome? By looking at the probabilities, we see that winning $0 has the highest probability, 0.5. So the most likely outcome is to win nothing. Third, what is the average result? To find this, we multiply each outcome by its probability and sum them. That's 0 times 0.5 plus 2 times 0.35, and so on, which gives us a total of $1.55. On average, a player wins $1.55 per game. Fourth, what would be a fair price to play the game? A game is considered fair if the average outcome, or expected value, for the player is 0. This would mean the cost to play should exactly equal the average winnings, which is $1.55, so the fair price is $1.55. These things to think about are the core concepts we'll be covering today. Let's start with the most basic building block. Our first learning objective is to define and distinguish between discrete and continuous random variables. To start, what exactly is a random variable? A random variable is a way to describe the numerical outcome of a random experiment. It's a variable because it can take different values, and it's random because its value is determined by chance. We often represent random variables with a capital letter, typically X. The key idea is that for every possible outcome of a random experiment, a random variable assigns it a single number. Random variables are split into two categories: discrete and continuous. A discrete random variable has a set of distinct countable possible values. The key word here is countable. The values don't necessarily have to be finite, but they can be listed out. To find the value of a discrete random variable, you count. A common example is the number of heads you get when you flip a coin several times. The number of heads can only be 0, 0, 1, 2, and so on. Another example is the number of customer complaints a company receives in a day. In contrast, a continuous random variable can take any value within a given interval. Its possible values are infinitely numerous and can't be listed. To find the value of a continuous random variable, you measure. Consider the height of a Year 12 student. Their height isn't just 120 or 170 centimeters. It could be 170.5 centimeters, 170.53 centimeters, 175.38 centimeters, and so on. The set of all possible heights forms a continuous interval. Other examples include the time it takes to complete a race or the temperature in a room. Let's work through an example to solidify our understanding of discrete random variables. Suppose a supermarket has 3 checkouts, A, B, and C. An inspector checks each checkout's weighing scale for accuracy. We define the random variable X as the number of accurate weighing scales at the supermarket. Our goal is to understand the possible outcomes and the corresponding values of X. First, let's list every possible outcome from inspecting the 3 scales. Let a checkmark symbol mean a scale is accurate and a cross mean it's not. Here's a table showing all 8 combinations. Now, let's assign a value of X, which is the number of accurate scales, to each outcome. For the first outcome, Ishatz, there are no accurate scales, so X equals 0. For outcomes with 1 accurate scale, like ATI, X is 1. We can see 3 such outcomes. Similarly, there are 3 outcomes with 2 accurate scales, so X is 2, and one outcome where all three scales are accurate, so x is 3. So the possible values for our discrete random variable x are 0, 1, 2, and 3. This means it's possible for there to be 0 accurate scales, 1, 2, or all three. Let's answer the follow-up questions. What values of x correspond to having exactly one accurate scale? From our table, this corresponds to x equals 1. What values correspond to having at least one accurate scale? At least 1 means 1 or more, so this corresponds to x being 1, 2, or 3. This example clearly shows how a random variable x maps complex outcomes of an experiment to simple, countable numbers. We have now reached the 10-minute mark. If you're looking for expert tuition to excel in your IB A-Level or IGCSE studies, don't hesitate to contact DAR tutors. Our experienced tutors are ready to help you achieve your academic goals. Let's move on to our next key topic, discrete probability distributions. Our second objective is to construct and interpret probability distributions. For any discrete random variable, there's a probability distribution that shows the probability of each possible value occurring. We use the notation P(x) equals x to represent the probability that our random variable x takes on a specific value, which we've called x. For example, Px equal 2 is the probability that the random variable x has a value of 2. There are two fundamental rules that every valid probability distribution must follow. First, the probability of any single outcome must be between 0 and 1, inclusive. You can't have a negative probability, and you can't have a probability greater than 1. Second, the sum of all the probabilities for all possible outcomes must equal 1. This means that if we list every single thing that can happen, their individual probabilities must add up to a certainty, or 100%. Let's illustrate this with an example, tossing two coins. We'll define x as the number of heads we get. What are the possible values for x? We can get 0 heads. Toss 1 head, ht or th, or 2 heads, hh. So x can be 0, 1, or 2. What are the probabilities? There are 4 equally likely outcomes. ht, tt. For x m 0, tt, the probability is 1 out of 4. For x epsilon 1, ht or th, the probability is 2 out of 4. For x celos 2, h, the probability is 1 out of 4. We can display this in a table. Notice that both rules are met. Each probability is between 0 and 1, and the sum of the probabilities is 1/4 plus 2/4 plus also 1/4 equals 1. This is a valid discrete probability distribution. There are some special types of discrete probability distributions we should be familiar with. First, a uniform discrete random variable is one where all the possible values have an equal chance of occurring. The probability for each of the n outcomes is simply 1 over n. The classic example is rolling a fair 6-sided die. The possible values are 1, 2, 3, 4, 5, and 6. There are 6 possible outcomes, and each has a probability of 1/6. This is a uniform distribution. Let's contrast that with rolling 2 dice and taking their sum. The possible values for the sum range from 2, 1 plus 1, to 12, 6, 6. However, the probabilities are not all the same. There's only one way to get a sum of 2, 1 plus 1. But there are 6 ways to get a sum of 7, 1 plus 6, 2 plus 5, 3 plus 4, etc. Since 7 is much more likely than 2, the sum of 2 dice is not a uniform discrete random variable. Next, let's talk about the mode and median of a discrete probability distribution. The mode is simply the value that occurs with the highest probability. It's the most likely outcome. The median is the value that corresponds to the 50th percentile. If we list the values in order, the median is the first value where the cumulative probability reaches or exceeds 0.5. Let's apply these concepts with an IB-style worked example. This will help us practice finding the mode and median. A magazine store recorded customer purchases for 1 week. 23% purchased 1 magazine, 38% purchased 2, 21% purchased 3, 13% purchased 4, and 5% purchased 5. Let X be the number of magazines bought by a randomly selected customer. First, let's state the possible values of X. Based on the problem statement, a customer can purchase 1, 2, 3, 4, or 5 magazines. So, the possible values for our random variable x are 1, 2, 3, 4, and 5. Next, let's construct a probability table. We convert the given percentages to probabilities. A purchase of 1 magazine has a probability of 0.23, 2 magazines has a probability of 0.38, and so on. We can quickly check that these probabilities sum to 1. Now, let's find the mode and median of this distribution. To find the mode, we look for the highest probability. The probability 0.38 is the largest, and it corresponds to x equals 2. Therefore, the mode is 2, meaning a customer is most likely to buy 2 magazines. For the median, we need to find the cumulative probability. Let's start from the left. The probability of buying 1 magazine is 0.23. The cumulative probability of buying 1 or 2 magazines is 0.23 plus 0.38, which equals 0.61. Since 0.61 is greater than or equal to 0.5, the median value is 2. So, the median number of magazines purchased is 2. So far, we've represented probability distributions with tables and bar graphs. We can also describe them using a function. A probability mass function, or PMF, is a function p of x that directly gives the probability for each possible value of the discrete random variable x. It's essentially a compact way to write down the distribution. Just like a probability table, a PMF must also satisfy the 2 rules for a valid probability distribution. First, for every x in the domain of the function, the probability p(x) must be between 0 and 1. Second, when you sum up p(x), for every possible value of x, you must get 1. Let's check this example. Is p of x equals x squared plus 1 all over 4 a valid PMF for x values 1, 2, 3, and 4? To verify, we'll check both rules. First, let's calculate the probability for each x value. For x minus 1, p1 is 2 over 34. For x or 2, p2 is 5 over 34. For x or 3, p3 is 10 over 34. And for x or 4, p4 is 17 over 34. We can see that all of these probabilities are between 0 and 1, so the first condition is met. Now, let's check the second rule. Do they sum to 1? Adding them up, we get 2 plus 5 plus 10 plus 17 all over 34, which is 34 over 4, or 1. The sum is 1, so the second condition is met. Both conditions hold, so Px is a valid probability mass function. A common type of problem in this topic is finding a missing probability. This is where the rule that probabilities sum to 1 becomes very powerful. Let's work through an example. Here is a probability distribution table. The probability of x as 0 is k, and the probabilities for x was 1, 2, and 3 are 2k, 3k, and k, respectively. Our goal is to find the value of k that makes this a valid distribution. We must use the rule that the sum of all probabilities is 1. So we add all the probabilities in the table and set the sum equal to 1. That's k plus 2k plus 3k plus k equals 1. Combining the terms, we get 7k equals 1. Solving for k, we find that k must be 17. Now we have the value of our constant. We can also calculate the individual probabilities. The probability for x of 0 is 17. For x of 1, it's 2 times 17, which is 2 is 7. For x of 2, it's 3, 7, and for x of 3, it's back to 17. We can quickly check that these values sum to 1. This method is crucial for many problems. We are now moving on to the final part of our learning objectives, calculating measures of center and spread. First, let's talk about the center. We've seen the mode and median. But the most important measure of central tendency for a probability distribution is the expected value, which we denote as E of x. The expected value is also known as the mean of the distribution and is sometimes represented by the Greek letter mu. Intuitively, the expected value is what we would expect to be the average outcome if we repeated the random experiment a very, very large number of times. To calculate the expected value, you multiply each possible value of the random variable by its corresponding probability, and then you sum up all of these products. So it's the sum of x sub I times p sub I, where x sub I are the values and p sub I are their probabilities. The expected value is a weighted average, with the probabilities serving as the weights. Let's revisit our magazine store example to calculate its expected value. Here's the probability table for the number of magazines, X. The expected value E of X is the sum of each value multiplied by its probability. Let's do the arithmetic. We get 0.23 plus 0.76 plus 0.63 plus 0.52 plus 0.25. Summing these values gives us 2.39. So, the expected number of magazines purchased is 2.39. Let's interpret what this means. The key is that the expected value itself doesn't have to be a possible outcome. You can't buy 2.39 magazines. What it tells us is that over a long period, if we looked at the average number of magazines bought per customer, it would be 2.39. While the expected value tells us the center of a distribution, it doesn't tell us about its spread. For that, we use variance and standard deviation. The variance, denoted as var of x or sigma squared, measures how spread out the values of a random variable are from its expected value. A large variance means the values are very spread out, and a small variance means they are clustered tightly around the mean. The variance is the expected value of the squared difference between the random variable and its mean. The formula for variance is the sum of each value x sub I minus the mean mu squared, all multiplied by its probability p sub I. This gives more weight to values that are further from the mean. This is the definition, and we'll use a more convenient computational formula later. The standard deviation, denoted by sigma, is simply the square root of the variance. Its main advantage is that it's in the same units as the random variable itself, making it easier to interpret. Like variance, a larger standard deviation indicates greater variability in the outcomes. Let's calculate the standard deviation for the magazine store example. Remember, our mean mu is 2.39. We need to calculate the sum of the squared differences times their probabilities. For each x value, we subtract the mean, square it, and then multiply by its probability. We do this for all x values and add them together. This calculation results in a variance of approximately 1.2579. Taking the square root gives us a standard deviation of about 1.12. So, on average, the number of magazines purchased deviates from the mean of 2.39 by about 1.12 magazines. This gives us a complete picture of the distribution's center and spread. Calculating variance using the definition formula can be tedious. Thankfully, there is an alternative and much more convenient formula. This formula states that the variance of x is equal to the expected value of x squared minus the square of the expected value of x. In other words, you find the sum of x squared times p and then subtract the mean squared. This avoids all the squared differences. Let's prove this. We start with the definitional formula for variance. We expand the term inside the summation. Then we use the property that the expectation of a sum is the sum of the individual expectations. This gives us three separate sums. The first sum is the definition of ex squared. The second sum is minus 2mu times the sum of xp, which is just ex, or mu, so that's minus 2mu squared. The third sum is mu squared times the sum of p, which is just mu squared, since the sum of probabilities is 1. Combining these terms, we get ex squared minus 2mu squared plus mu squared, which simplifies to ex squared minus mu squared, proving our formula. Let's use this alternative formula to recalculate the variance for our magazine store problem. The mean mu is 2.39. We already calculated it. Now we need to find ex squared. We square each x value, multiply it by its probability, and sum them up. Calculating this gives us 6.97. Now we can find the variance. Variance is ex squared minus the mean squared, which is 6.97 minus 2.39 squared. This gives us approximately 1.2579, the exact same result we found before, but with less work. We can also see how these calculations are done using a graphics calculator, which is essential for the IBAI-HL exam. Most calculators will have a statistics mode that can compute the mean and standard deviation directly. Let's demonstrate with our magazine store data. First, you need to enter your data. Typically, you'll go into your calculator's stat mode and select Edit. In one list, say L1, you'll enter the X values, 1, 2, 3, 4, 5. In another list, L2, you'll enter the corresponding probabilities. 0.23, 0.38, 0.21, 0.13, 0.05. Once the data is entered, you'll go to the Stat mode, select Calc, and choose one var stats or one variable statistics. Here's the crucial step for probability distributions. You must specify your X list, L1, and your frequency list. For a probability distribution, the probabilities act as the frequencies. So you'll select L2 as your frequency list. If you forget this step, your calculator will treat all X values as equally likely, and you'll get the wrong answer. When you hit Calculate, you'll get a screen like this. Notice the value for X bar, which represents the mean. It's 2.39, matching our manual calculation. And the value for sigma X, which is the standard deviation for the entire population, our probability distribution, is 1.1215, matching our result. Using the calculator saves a lot of time and reduces calculation errors, which is invaluable in an exam. Our final topic is understanding the properties of linear transformations of random variables. This is a very common type of question on the IBHL paper. Suppose you have a random variable x and you create a new random variable y by a linear transformation. Y equals ax plus b. Here, a and b are just constants. The question is, how are the expected value and variance of y related to the expected value and variance of x? Let's start with the expected value. The formula for the expected value of y equals ax plus b is simply a times the expected value of x plus b. The mean of a linear transformation is the linear transformation of the mean. So you can find the mean of x, multiply it by a, and add b. The variance behaves differently. The formula for the variance of y equals ax plus b is a squared times the variance of x. Notice two things. The constant b disappears, and the constant a gets squared. Adding a constant b shifts the entire distribution, but it doesn't change its spread. However, multiplying by a scales the spread, and the variance is a squared measure of spread. So a must be squared as well. From the variance, we can easily find the standard deviation. Since standard deviation is the square root of variance, the standard deviation of y is the square root of a squared times the standard deviation of x. This simplifies to the absolute value of a times the standard deviation of x. The absolute value is crucial because standard deviation must always be non-negative. Let's work through an example to see these properties in action. Suppose we have a random variable x with a mean of 8.1 and a standard deviation of 2.37. A new random variable y is defined by the transformation y equals 4x. 7. We need to find the mean and standard deviation of y. We'll use the properties we just learned. First, for the mean, e of y equals e of 4x minus 7. Using the property for the expected value of a linear transformation, this is equal to 4 times e of x minus 7. Substituting the known value for e of x, we get 4 times 8.1 minus 7. Calculating this, we find that the mean of y is 25.4. Now for the standard deviation. We need the standard deviation of 4x minus 7. Using the property for standard deviation, this is equal to the absolute value of 4 times the standard deviation of x. We substitute the given standard deviation of x. 4 times 2.37 is 9.48, so the standard deviation of y is 9.48. You can see that finding the mean and standard deviation of y was very efficient. We didn't need to create a probability distribution for y at all. We just applied the properties to the mean and standard deviation of the original variable x. We've covered all the core concepts of discrete random variables. Now let's practice with some IB-style questions to solidify your understanding. Here is our first problem. A tetrahedral die has faces labeled 1, 2, 3, and 4. Let x be the number rolled when the die is rolled once. Let y be the highest number rolled when the die is rolled twice. The question asks two parts. First, would you expect the mean of y to be greater than the mean of x? Second, would you expect the standard deviation of y to be greater than the standard deviation of x? Explain your answers. Take a moment to think about this. What happens when you roll the die a second time? Let's consider the mean first. When we roll once, x can be 1, 2, 3, or 4. The mean will be the average of these. When we roll twice and take the highest, the possible values for y are still 1, 2, 3, or 4. However, the outcomes 1 and 2 are much less likely for y. For example, to get a 1 for y, both rolls must be 1. To get a 4 for y, any roll with a 4 would be a 4. This means the distribution for y will be skewed towards the higher values. Therefore, we would expect the mean of y to be greater than the mean of x. Now for the standard deviation. The standard deviation measures spread. For x, the outcomes are spread from 1 to 4. For y, the outcomes are less spread. The probability of getting a 1 is very small, and the probability of getting a 4 is high. The other values, 2 and 3, are still possible, but their probabilities are less than for x. This means the values for y are more concentrated around the upper end of the range and less spread out overall. Therefore, we would expect the standard deviation of y to be less than the standard deviation of x. Let's continue with the second part of this problem. This part requires a more detailed calculation. We need to construct the probability distributions for x and y, and then calculate their means and standard deviations to confirm our predictions. Let's start with x, the number rolled on a single die. The values are 1, 2, 3, 4, each with a probability of 1/4. We can calculate the mean and variance. The mean is 2.5. The variance, using the alternative formula, is 1.25. The standard deviation is the square root of 1.25, which is approximately 1.1. Now for y, the highest number from 2 rolls. We need to list the outcomes and find their probabilities. When rolling twice, there are 4 times 4, or 16, equally likely outcomes. For y1, only 1 to 1 works, so y1 is 1/16. For y2, outcomes are 1/2, 2/1, 2/2, so y2 is 3/16. Similarly, y3 is 5/16 and y4 is 7/16. Let's check. 1 per 3, 5, 7 equals 16, so the probabilities sum to 1. Now we calculate the mean and standard deviation for y. The mean E of y is 3.125. This is indeed greater than 2.5, confirming our prediction. The variance is 0.609. The standard deviation is 0.781, which is less than 1.118, also confirming our prediction. Let's try a second IB-style question. Dominic is a door-to-door salesman. Each day he earns a base salary of $100 plus $25 for each sale made. Let x be the number of sales Dominic makes in a day. The probability distribution for x is given in this table. Our task is to analyze his earnings. First, we find the expected number of sales, the variance of the number of sales, and the standard deviation. The expected number of sales, E of x, is calculated by multiplying each number of sales by its probability and summing them up. This gives us 2.06. This means Dominic is expected to make 2.06 sales per day, on average. The variance, calculated as EX squared minus EX squared, is 1.6364. The standard deviation is the square root of the variance, which is approximately 1.279. This measures the typical deviation in his daily sales. Now let's look at his earnings. We'll define a new random variable y for his total earnings in dollars per day. The problem states he earns $100 plus $25 for each sale, x. So y is a linear transformation of x given by y equals 25x plus 100. Finally, we'll find the mean and standard deviation of his earnings, using the properties we learned. The expected earnings, E of y, is 25 times the expected sales E of x plus 100. Plugging in 2.06 for E of x, we get 251.50. So, Dominic expects to earn $251.50 per day. The standard deviation of earnings, sigma of y, is the absolute value of 25 times the standard deviation of sales, sigma of x. This is 25 times 1.279, which gives us approximately 31.98. This tells us the typical daily variation in his earnings. His standard deviation is larger, which is expected since the values are multiplied by 25. Here is our third IB-style practice problem, involving finding unknown constants in a probability distribution. Given that the expected value E of x is 2.5, we need to find the unknown probabilities A and B in the table. Since we have two unknowns, we'll need to set up a system of two equations. The first equation comes from the rule that the sum of all probabilities must be 1. So, 0.3 plus A plus B plus 0.2 must equal 1. This simplifies to a plus B equals 0.5. This is our first equation. The second equation comes from the definition of the expected value. We are given E of x is 2.5, so the sum of x times P of x, which is 1 times 0.3 plus 2 times A plus 3 times B plus 4 times 0.2 must equal 2.5. This simplifies to 2A plus 3B equals 1.4. This is our second equation. Now we have a system of two linear equations with two variables. From the first equation, we can express A as 0.5 minus B. We substitute this into the second equation. After distributing and simplifying, we get that B equals 0.4. Substituting B back into the first equation, we find that A equals 0.1. So the missing probabilities are A equals 0.1 and B equals 0.4. Our fourth practice question deals with a concept called fair games. An insurance policy covers a $20,000 sapphire ring against theft and loss. If stolen, the company pays $20,000. If lost, they pay $8,000. The probability of theft is 0.02 and the probability of loss is 0.03. The question is, how much should the company charge to cover the ring so that their expected return is $100? In other words, after many policies, the company wants to make an average profit of $100 per policy. Let's define a random variable x for the company's return. X is the return, which is the premium they charge minus any payouts. What are the possible outcomes for the company? The ring could be stolen, lost, or neither. Let's call the premium X. If the ring is stolen, the company pays $20,000, so their return is X minus $20,000. This happens with probability 0.0025. If the ring is lost, they pay $8,000, so their return is X minus 8 yen. This happens with probability 0.03. If nothing happens, the probability is 1 minus the sum of the other two, which is 0.9675. In this case, their return is simply X, the premium they charged. We want the expected return, EX, to be 100. We set up the equation for expected value. We multiply each return by its probability and set the sum equal to 100. This gives us 0.0025 times the quantity X minus 20,000, plus 0.03 times the quantity X minus 8,000, plus 0.9675 times X equals 100. Now we solve for X. Distribute the probabilities, combine the X terms, and move the constants to the right side. This gives X minus 290 equals 100. Solving for X, we find X equals 390. So, to make an average profit of $100 per policy, the company should charge a premium of $390. Our fifth and final practice question builds on the idea of fair games and expected value. A person selects a disc from a bag containing 10 black discs, 4 blue discs, and 1 gold disc. The game costs $4 to play. The player wins $1 for a black disc, $5 for a blue disc, and $20 for a gold disc for a sup-up. Part A asks us to calculate the expected gain for the player and show that the game is not fair. Part B asks, if the game is made fair by increasing the prize for a gold disc, what should the new prize be? First, let's find the total number of discs, which is 10 plus 4 plus 1, equaling 15. The cost to play is 4. For Part A, we calculate the player's expected gain, which is E winnings minus the cost. The probability of winning $1 with a black disc is 10/15. The probability of winning $5 with a blue disc is 4/15. And the probability of winning $20 with a gold disc is 1/15. Let's calculate the expected winnings. We multiply each prize by its probability and sum them. The expected winnings are 10/3, which is about $3.33. The expected gain is the expected winnings minus the cost, so 10 by 3 minus 4, which is -2/3. Since the expected gain is not 0, the game is not fair. A player is expected to lose 2/3 of a dollar, or about 67 cents per game on average. Now for Part B. Find the new prize for the gold disc to make the game fair. Let the new prize for the gold disc be X. For the game to be fair, the player's expected gain must be 0. This means the expected winnings must exactly equal the cost of $4. We set up a new expected winnings equation with the unknown X. 1 times 10, 15, plus 5 times 4, 15, plus our new prize X times 1, 15. This sum must equal 4. We simplify the equation. Solving this equation for X, we get 30 plus X equals 60, which means X equals 30. So, to make the game fair, the prize money for selecting the gold disc must be increased to $30. This ensures that in the long run, players will break even. Let's quickly recap what we've learned today. We started by defining a discrete random variable as a variable with countable outcomes and distinguished it from a continuous random variable. We learned how to build a probability distribution for a discrete random variable, ensuring it follows the rules that probabilities are between 0 and 1 and sum to 1. We then explored measures of central tendency like the mode and median, and the all-important expected value, which represents the long-term average. To describe the spread of a distribution, we learned about variance and standard deviation, including the alternative, more convenient formula. Finally, we studied the properties of linear transformations, which allow us to quickly find the mean and standard deviation of a new variable without recalculating from scratch. I hope these examples and explanations have been helpful. Remember, mastering these foundational concepts is key to success in IB mathematics. Thank you for watching. Once again, if you need more personalized support, whether it's through online or in-home tuition for IB, A-Level, or IGCSE, please contact DAR Tutors. Our dedicated team is here to help you succeed.